A new test stand has just been installed on the Orbital Launch Mount, signaling the start of a series of powerful tests. With each component now falling into place, the next Starship launch is drawing near. At the same time, SpaceX's Falcon 9 has launched a payload to orbit on behalf of Jeff Bezos' company, supporting the deployment of its satellite network. Across the globe, China has also marked a significant milestone, successfully delivering new generation spacesuits to the Tiangong space station. These suits are a key part of their broader preparations for a set of bold and highly ambitious missions. It can now be said with confidence that the new static fire test stand has become the centerpiece of attention at Starbase. Since its debut a few weeks ago, anticipation has steadily grown for its integration with the Orbital Launch Mount, and that moment has finally arrived. This milestone marks a pivotal step forward in SpaceX's rapid preparations for the next Starship mission. Signs of this development emerged on the 16th of July when observers noticed that the ship quick disconnect arm retracted from its usual position, creating room for the chopsticks system to operate. The QD arm later returned to place, signaling that a lift operation was being readied. By the morning of the 17th, the heavy-duty crane stationed at Pad B had been moved to Pad A, confirming that the long-awaited installation was imminent. The lift commenced early on the 18th, and within 30 minutes, the test stand was successfully placed atop the OLM. Later that same day, the crane disengaged, confirming that the stand was securely in position. Although successfully installed, the structure still requires reinforcement and final adjustments before operations can begin. SpaceX had previously added supporting legs to the frame, which are likely to be bolted into place to maintain flexibility for future modifications. This approach aligns with SpaceX's emphasis on modularity and speed when executing upgrades or replacements. This installation completes one of the final major pieces of the Orbital Launch Mount's transformation. What once stood as a simple structural ring has evolved into a reinforced, feature-rich platform, outfitted with Raptor vacuum engine mounts, leg supports, and steel reinforcements for added durability. Additional components, such as the ship QD frame and fuel pipe systems, have also been steadily upgraded to provide reliable propellant flow during upcoming test campaigns. With the stand now secured, attention shifts to finishing the QD panel and integrating the remaining systems required for operation. Meanwhile, S-37 has been undergoing final engine installations over the past several weeks, and all signs point to the vehicle being fully outfitted. The recent removal of the ship's dedicated transport stand suggests that a standard transport rig will soon be used to move S-37 to the pad, where it will be lifted onto the newly installed stand for alignment checks and system validations. Once in position, Ship 37 is expected to begin a two-phase static fire testing sequence. The first test will likely involve a single engine burn, acting as a systems demonstration for the new test stand and quick disconnect system. This low-risk trial will allow engineers to verify fuel flow, ignition readiness, and safety systems without subjecting the hardware to prolonged stress. Assuming success, the team will move forward with a full-duration static fire lasting close to 1 minute. This extended burn will push the engines to their operational limits, testing thrust output, gimbal movement, and thermal resilience. Engineers will closely monitor all parameters to confirm that the entire vehicle support system stack is ready for the challenges of flight. Given the current pace, these tests are anticipated to take place between the 21st and the 27th of this month, aligning with expectations for the fourth week of the month. Following the static fire campaign, S-37 will be returned to Mega Bay 2 for final inspections and any required adjustments. After this post-test phase, the vehicle will proceed to final integration for flight. If all remains on schedule, the next Starship launch could take place in early August, consistent with both internal SpaceX goals and FCC filings. These advancements are especially notable in the wake of the S-36 failure, which had cast doubt on whether a quick recovery was possible. However, through fast-paced innovation and decisive action, SpaceX has not only regained momentum, but has done so in a way that reinforces its commitment to continuous improvement. The new static fire stand is a core component of that recovery, acting as both a technical asset and a symbol of SpaceX's rapid problem-solving culture. As the new test infrastructure enters its final stages of readiness and S-37 stands nearly prepped for testing, SpaceX appears well positioned to enter the next phase of its Starship program. The coming days are expected to bring critical verification tests with the promise of a flight-ready system shortly thereafter. This milestone not only paves the way for Flight 10, but also sets a new standard for how quickly and efficiently major upgrades can be implemented and deployed. If you're excited for what's ahead, type 10 in the comments and be sure to like and subscribe to stay in the loop on every update in SpaceX's thrilling journey. In the quiet hours of July 16th, at exactly 2:30 in the morning local time, a Falcon 9 rocket pierced the skies above Cape Canaveral, Florida, lifting off from Space Launch Complex 40. On board were 24 Kuiper satellites destined for low Earth orbit, in a mission that marked the beginning of an unexpected collaboration between two titans of the modern space race, SpaceX and Amazon. This flight was the first of 3 contracted missions that Amazon awarded to SpaceX in late 2023, despite a history of fierce rivalry between the company's founders. The rocket's first stage, B-1096, performed flawlessly on its maiden flight, returning just over 8 minutes later to land gracefully on the drone ship A Shortfall of Gravitas, stationed in the Atlantic. Its successful recovery further solidified SpaceX's unmatched reputation for reusable launch technology. Nearly an hour after launch, confirmation followed that all 24 Kuiper satellites had been successfully deployed at an initial altitude of 289 miles or approximately 465 kilometers. The entire deployment process took just 8 minutes. From there, the satellites are programmed to maneuver into their designated operational orbit, located roughly 392 miles or about 630 kilometers above the Earth. This marks the 3rd official launch in Amazon's Kuiper initiative, which is designed to create a vast constellation of broadband internet satellites aiming to directly compete with SpaceX's already dominant Starlink network. While Starlink boasts nearly 8,000 operational satellites and sees new launches almost weekly, Amazon's Kuiper system is still in its early stages. The 2 previous Kuiper missions were carried out using ULA's Atlas V rocket in April and June. Amazon ultimately intends to deploy more than 3,200 satellites over at least 80 launches in the years ahead. That SpaceX is now actively supporting the Kuiper rollout is nothing short of remarkable. Until recently, Amazon had made deliberate efforts to exclude SpaceX from the Kuiper launch provider pool. Instead, the company turned to Blue Origin, ULA, and Europe's Arianespace to carry out its deployment plans. But complications quickly surfaced. Blue Origin's New Glenn rocket, one of Amazon's top picks, only launched for the first time earlier this year. With no clear timeline for subsequent missions and a growing focus on lunar and deep space projects for NASA, Blue Origin became an unreliable option for the Kuiper schedule. Arianespace encountered its own struggles during the transition from the retired Ariane 5 to the new Ariane 6. Though Ariane 6 holds promise, it has launched only twice so far, both missions raising concerns about the rocket's performance and its readiness for sustained operations. ULA, once considered a reliable partner, is facing similar limitations. Their 2 Kuiper missions relied on the aging Atlas V, which is nearing retirement. The rocket's successor, the Vulcan Centaur, has flown only twice and is currently more aligned with military contracts than commercial launches. Faced with mounting delays and an urgent need to stay relevant in the fast-moving satellite and internet market, Amazon pivoted. In late 2023, the company quietly signed a deal with SpaceX to launch 3 batches of Kuiper satellites aboard Falcon 9. It was a decision born of necessity, but one that unmistakably highlighted SpaceX's dominance in the launch sector. Few providers can match the reliability, frequency, and cost-effectiveness that SpaceX now offers with Falcon 9 and its recovery-capable boosters. This mission also reflects a deeper confidence from SpaceX, a willingness to launch a competitor's assets into orbit without hesitation. That speaks volumes about the company's maturity and belief in its own technological edge. Starlink continues to lead the market in infrastructure, scale, and performance. By agreeing to help Amazon deploy Kuiper satellites, SpaceX essentially said, "We're not just confident in our systems, we are unshaken by competition." Had Amazon partnered with SpaceX from the start, the Kuiper constellation would likely be far more developed by now. Instead, the company is playing catch-up. With Blue Origin, ULA, and Arianespace all still ironing out their own issues, there is growing speculation that Amazon will need to further extend its partnership with SpaceX. If so, this development could push other launch providers to accelerate progress and resolve setbacks, potentially fueling healthy competition in the global space economy. This particular mission also carried symbolic weight. It was SpaceX's 87th Falcon 9 flight of the year, bringing the company closer to matching the total number of launches it completed in all of 2024. With an ambitious goal of surpassing 180 launches this year, the momentum is undeniable. Adding to the historical resonance, the launch took place on the 56th anniversary of the Apollo 11 mission, the moment when humans first landed on the moon. The alignment of this modern commercial success with one of the most iconic moments in space history, was not lost on those following the event. It was a quiet reminder of how far the industry has come and how companies like SpaceX are redefining the limits of possibility. Meanwhile, halfway around the world, China was making headlines of its own. On the 14th at 5:34 p.m. Eastern, early morning local time on July 15th, the country launched a Long March 7 rocket from the Wencheng Satellite Launch Center on Hainan Island. On board was the Tiangong 9 cargo spacecraft, which carried a payload of roughly 7.2 tons of supplies to the Tiangong space station. The delivery included food, fuel, equipment, and notably 2 new generation extravehicular mobility suits, spacesuits that represent a major leap forward for the Chinese space program. According to reports from Chinese media, the new suits can support up to 4 years of service and enable up to 20 spacewalks, a significant upgrade from the previous design, which lasted for 3 years and allowed 15 EVAs. The shipment also included advanced exercise equipment to help astronauts combat muscle atrophy that can occur during extended stays in microgravity. These upgrades suggest that China is preparing for more ambitious undertakings in low Earth orbit and beyond. While there has been no official confirmation, many observers believe the new equipment could be laying the groundwork for future lunar missions, or perhaps even more distant goals. As the Chinese space program gains momentum, it is becoming increasingly clear that the global space race is no longer a one-sided affair. America's lead remains firm for now, but sustained innovation and strategic investments will be essential to maintain it. So, is the modern space race entering a new chapter? With SpaceX launching a competitor's constellation, Amazon shifting alliances, and China steadily expanding its reach, the answer seems obvious. A new era is unfolding, one that is more competitive, more collaborative, and more global than ever. If you enjoyed this update, make sure to like the video and subscribe for more news and insights from the world of space exploration, only with Great SpaceX. A section of Booster 13 has been pulled from the ocean, offering SpaceX a rare chance to analyze hardware exposed to the extreme forces of launch and splashdown. This recovery could reveal valuable insights into reusability and structural resilience. At Starbase, the test campaign continues at full tilt. Each operation brings Starship closer to its next flight, with activity ramping up across the launch complex, a clear signal that major milestones are fast approaching. Meanwhile, South Korea is stepping into the lunar spotlight. The nation is advancing plans to join the global effort to establish a moon base, staking its claim in the next great leap of exploration. It is often said that the true marvel of SpaceX's Starship program lies not just in its powerful launches or spectacular test flights, but in the stories that unfold after the engines go silent. Among the most compelling are the ocean recovery missions, efforts that transformed sunken wreckage into priceless source of data. Over the past year, we have seen SpaceX retrieve critical hardware from the sea, including the famous recovery of B-11 from Flight 4. That operation made waves after Musk described the corroded booster as resembling a remnant of an ancient civilization. Now, a similar chapter unfolds with the recovery of B-13 from Flight 6. The first sign of success came with a striking image, the aft section of B-13 being hoisted from the ocean by a towering crane, lifted onto a transport vessel. Carefully wrapped in its protective fabric, the booster began its journey back to shore, 8 months after its descent into the sea. Despite prolonged submersion and the corrosive effects of salt water, the core of the structure remained impressively intact. This aft section, home to critical components like Raptor engines, fuel lines, and pressure vessels, had weathered the elements well, far better than many anticipated. Flight 6 paired B-13 with S-31, a vehicle that completed what many regard as the most successful Starship landing to date. Unfortunately, B-13 suffered from a communications failure during descent, which led to the booster executing a controlled splashdown rather than a powered landing. Just like with B-11, what has now been recovered is the rear segment of the vehicle, the very heart of its propulsion and plumbing systems. Once again, Musk noted that the remnants looked like the ruins of a long-dead civilization, a poetic nod to the scorched and eroded hardware. Visual evidence from the recovery effort already speaks volumes. While a few Raptor nozzles appear bent or broken, many engines seem remarkably well preserved. Mud, grime, and discoloration cover the structure, but underneath the surface, vital systems like fuel conduits and composite overwrapped pressure vessels remain largely intact. Some parts of the structure show signs of deformation, potentially from the forceful impact or the strain of being separated from the rest of the booster. Yet the overall condition defies expectations for a vehicle pulled from the ocean after so many months. The Raptor engines offer an especially valuable look into post-mission performance. Cracked nozzles and exposed upper engine assemblies, though damaged, still reveal structural details rarely seen outside of blueprints. This gives engineers a rare opportunity to observe how real-world conditions, like ignition, flight stresses, splashdown forces, and long-term exposure to salt water, affect some of the most sophisticated rocket systems in existence. With this portion of B-13 now on its way back to land, SpaceX engineers will soon have the chance to conduct a far more detailed analysis. It is expected that the aft section will be transported to one of the company's key facilities, most likely in Texas, where thorough inspections will begin. By comparing the condition of individual systems, those that held up, those that corroded, and those that failed entirely, SpaceX can refine its designs and reinforce the most vulnerable components in future builds. Although Flight 6's failure was not directly caused by a flaw in the booster, understanding the physical toll of splashdowns allows SpaceX to make better decisions going forward. It's this commitment to learning from every outcome that sets the company apart. Every piece of recovered wreckage is not treated as a failure, but as a data-rich artifact that can drive the next innovation. Attention is now turning to B-14, which flew during Flight 9 and met a more abrupt end than its predecessor. If recovered, it could yield even deeper insights. Given SpaceX's increasing focus on ocean retrievals, efforts to locate and extract B-14 may already be underway. Still, ocean landings are not the final goal. SpaceX envisions routine recoveries using the Mechazilla arms, which means catching boosters midair and setting them directly on the launch pad for rapid reuse. This represents true reusability. Minimal damage, minimal delay. Until then, recoveries like that of B-13 remain vital. They turn failure into opportunity, offering lessons that make the next vehicle even more resilient. Each wrecked booster tells a story of iteration, ambition, and the drive to redefine spaceflight. While recovery efforts at sea continue, momentum is rapidly building at Starbase as preparations for Flight 10 near their final stages. Central to this progress is the ship quick disconnect system at Pad A, which is almost fully assembled. The last key piece, the interaction panel that links directly to the ship, is expected to be installed within days. Once in place, this will complete one of the final upgrades needed to support upcoming launch operations. Simultaneously, Ship 37 is making significant strides inside Megabay 2. Observers recently spotted its forward flaps, a clear indication that installation is imminent. Notably, these flaps were absent during cryogenic testing back in May, suggesting a methodical, staged approach to the vehicle's final integration. With internal systems verified and the engine section already in place, S-37 is nearly ready to be transported. Once the flaps are attached and Pad A's QD system is fully operational, the path will be clear for rollout to the launch site. Just across from Pad A, Pad B is also seeing rapid advancements. On July 19th, SpaceX delivered and installed a new methane quick disconnect arm designed for super heavy fueling. This large, intricate structure was secured in place within the same day, underscoring SpaceX's pace. Though its final configuration is still evolving, the arm bears a strong resemblance to the QD arm already in service at Pad A, complete with exposed beams and complex piping that will likely be refined further. Positioning at the top of the booster QD tower, this component is essential for the pad's upcoming role in booster operations. With the methane QD arm now installed, Pad B is edging closer to becoming fully functional. Initial subsystem testing could begin soon, potentially followed by full-stack booster tests. All indications point to Pad B playing a crucial role in the next phase of SpaceX's campaign. Meanwhile, attention is also fixed on B-18. The first of the version 3 Super Heavy class. It has already undergone partial outfitting, including the installation of a fuel transfer tube. However, its forward section has not yet been attached. This highly anticipated component is expected to feature several key upgrades, including a redesigned hot staging ring and a new grid fin layout. A recent image from the Star Factory has provided a glimpse of this forward section. While the photo only reveals the structure above the hot staging ring, the visible details align closely with renders shown during SpaceX's latest presentation. The new staging ring appears streamlined and optimized for efficiency, key traits for boosting performance in the V3 series. Though SpaceX has yet to confirm the section's identity, all signs suggest it belongs to B-18. If true, the full stack could be assembled in the next 1 to 2 weeks, marking a major step toward next-gen booster testing. The steady march toward Flight 10 and the development of B-18 reflects SpaceX's relentless drive to evolve. As hardware advances and infrastructure nears readiness, a bold new chapter for Starbase is about to unfold. Now, let us move on to a surprising and ambitious update from South Korea regarding its plans for lunar exploration. When people think about the modern space race, especially the efforts to reach and settle on the moon, a few familiar names often dominate the conversation. The United States, Russia, China, and the European Union have long been at the forefront. More recently, India and Japan have also joined the list of major contenders. However, the race is expanding. New players are stepping into the spotlight, and South Korea has now emerged as one of the most noteworthy newcomers. On the 17th of July, the Korea Times reported that South Korea is aiming to build a moon base by the year 2045. This bold vision was revealed during a public hearing hosted by the National Research Foundation of Korea in the city of Daejeon. During the event, representatives from the newly established Korea Aerospace Administration, also known as KASA, laid out an extensive long-term space exploration roadmap. According to the Korea Times, this roadmap includes 5 core missions. These cover activities in low Earth orbit, microgravity research, lunar exploration, solar studies, and broader space science missions. This declaration places South Korea among the few nations that have announced a firm timeline for building a lunar base. Interestingly, this goal comes even earlier than India's recently declared target of establishing a moon base by 2047. While many major powers like the US, Russia, China, and Japan also plan to set up lunar habitats, their timelines often point to the next decade or later. South Korea's plan, therefore, positions it as a highly ambitious and fast-moving entrant in this expanding field. In support of its lunar vision, South Korea has already begun laying the groundwork. For instance, the Korea Institute of Geoscience and Mineral Resources has taken early steps by deploying prototype lunar rovers in an abandoned coal mine. These tests are aimed at developing technologies that could be used for space mining in the future, an area of growing interest among spacefaring nations. Additionally, South Korea has already achieved a notable milestone with its first mission to lunar orbit. In August of 2022, the country launched the Korea Pathfinder Lunar Orbiter, also known as Danuri, aboard a SpaceX Falcon 9 rocket. The spacecraft successfully entered lunar orbit 4 months later and continues to operate, studying the moon with its scientific instruments. Prior to this new roadmap, South Korean officials had already announced their intention to land a robotic spacecraft on the moon by 2032. However, the newly unveiled timeline pushes their ambitions even further. The country now plans to develop a more advanced lunar lander by 2040, with the ultimate goal of establishing a lunar economic base by 2045. This expansion in scope suggests a growing confidence in the nation's ability to contribute meaningfully to humanity's presence on the moon. Despite these big goals, it is important to remember that South Korea is still relatively new to deep space exploration. The country faces significant challenges due to its later start and limited experience compared to established space powers. However, its recent achievements and detailed planning show that it is approaching the challenge with seriousness and determination. Only time will tell how far South Korea can go in this increasingly competitive race to the moon. But one thing is clear: the nation is aiming high, and its entrance adds fresh energy to humanity's collective dream of building a future on the lunar surface. Let us wait and see how South Korea's bold vision unfolds in the years to come. A new beach closure has just been announced, possibly signaling the long-awaited static fire test of Ship 37. Excitement is building, but when exactly will the test take place? Meanwhile, B-13 has returned home and is already being prepared for its next chapter. Over on the Falcon 9 front, a power outage has delayed one of its upcoming missions. And across the globe, Europe has successfully completed a parachute trial for a future Mars landing, marking a key step forward in interplanetary exploration. We are now in the final stretch of July, and preparations for Flight 10 are fully underway. Among the many exciting developments, the event that has captured the most attention is the upcoming static fire test of Ship 37. While progress updates provides a general sense of momentum, it is the official testing schedule that offers true clarity. Fortunately, we now have one. A new beach closure has just been announced for Boca Chica, scheduled for the 29th of July. Although the exact timing of the closure has not yet been disclosed, the date falls early next week, which aligns well with expectations for a major test event. Typically, when a closure of this nature is issued, it signals a significant activity at the launch site. In this case, it is likely related to the test stand at Pad A, where SpaceX recently completed the installation of upgraded test systems. The question now is which prototype will undergo testing during this window. There are currently 2 candidates, Ship 37 and 38. 37 is the leading contender for the static fire test. It has completed engine installation, flap attachment, and other key outfitting steps, which means it is essentially ready to be rolled out for final preparations. 38, on the other hand, is being readied for cryogenic testing. The latest visual updates show ongoing work on its nose cone, which appears to involve heat shield-related tasks. The removal of scaffolding around the vehicle also signals that it is entering the final phase of its pre-test setup. There is a strategic reason why SpaceX might choose Ship 38 for the first test. Conducting a cryogenic test before a static fire could help verify the performance and safety of the newly installed test systems. A test like this would allow engineers to validate the readiness of hardware in a lower-risk environment before subjecting it to the intense forces generated by a live engine firing. However, I still believe that this upcoming closure points toward a static fire test for Ship 37. Both Musk and previous FCC filings have estimated that Flight 10 could take place in early August. Given that we are already approaching the end of July, the timeline is tight. Any further delays could jeopardize that launch window. Moreover, there is a strong argument that the extensive testing of the systems may not be entirely necessary. The Orbital Launch Mount has already proven itself capable of handling the forces involved in booster tests and full-scale launches. A ship-level static fire, which produces significantly less thrust, should be well within its operational limits. The new ship quick disconnect system and updated piping infrastructure are based on proven OLM designs, while the water deluge system will draw directly from the robust platform beneath the mount. The only potential concern lies in the integration of these new and old systems, but even this is manageable, especially when you consider SpaceX's rapid iteration philosophy and its ability to implement on-the-fly improvements. If the static fire proceeds as expected, it will not be the only test we can anticipate. Based on past patterns, Ship 37 could undergo multiple tests, which might include a brief single-engine ignition followed by a full-duration multi-engine firing that could last up to 1 minute. These trials are crucial not just for validating flight readiness, but also for pushing the vehicle to its limits and uncovering any hidden issues early. Looking ahead, several steps still need to be completed to keep things on track. Final connections must be made to the piping systems at the test site. These will need to be integrated with the ship's quick disconnect panel. Meanwhile, S-37 itself will undergo a comprehensive review to ensure all systems are functioning properly before it can be transported. Speaking of transportation, the stand required to move Ship 37 must also be relocated to Mega Bay 2 in preparation for rollout. All of this work is expected to wrap up within the next few days, setting the stage for what could be one of the most critical and thrilling weeks yet in the Starship program. So, are you ready for the next big test? If you are, comment "Let's do it" below. Be sure to like the video and subscribe to our channel to stay updated on every step of SpaceX's incredible journey. Now, let us turn our attention to another major highlight in recent Starship developments, B-13. B-13's dramatic recovery continues to shape Starship's future. Its aft section, easily identified by 3 prominent engine mount spikes, has officially arrived at the port of Brownsville after being raised from the ocean floor. Striking new images captured the booster's condition during its maritime journey, offering rare insights into the aftermath of its descent. The section is now being prepared for transfer to SpaceX's Starbase facilities. A road closure from midnight to 4 a.m. on July 23rd was scheduled to support this move, meaning the booster may already be en route or undergoing detailed inspection as you watch this. While its condition has already been discussed, the real value lies in what comes next. Once at Starbase, engineers will conduct a thorough analysis of the structure. Any salvageable components may be reused or studied, while damaged elements will inform design improvements. These findings are essential to understanding the forces the booster endured during flight, descent, and impact. B-13's lessons are particularly important for the upcoming Flight 10, which will feature B-16. This next launch will introduce new challenges, including advanced flip maneuvers and steeper landings. Data from B-13 will directly enhance reliability and control for its next step in the Starship program. Beyond Flight 10, B-13's recovery feeds into the broader evolution of Starship. Inside the Mega Bay, the V3 architecture is already under construction, incorporating refinements driven by post-flight assessments like this one. Every piece of recovered hardware tells a story, and this one may prove pivotal in Starbase's journey toward full reusability and mission success. Now, moving from Starbase to another important development, let us discuss the recent Falcon 9 mission that was unexpectedly scrubbed. That particular Falcon 9 launch carried a suite of scientific payloads, including NASA's Tracers satellites. It was unexpectedly scrubbed just 45 seconds before liftoff. The mission, part of SpaceX's rideshare program, was set to launch from Vandenberg Space Force Base, but was halted due to a no-go condition issued by the FAA. The root cause? A regional power outage in Santa Barbara disrupted telecommunications at the Los Angeles Air Route Traffic Control Center, which oversees flight paths over the Pacific. As a safety precaution, the FAA postponed the launch to ensure safe airspace operations. While rare, this incident highlights how deeply spaceflight depends on terrestrial infrastructure. SpaceX acknowledged the delay and has rescheduled the launch for July 23rd at 11:13 a.m. Pacific Daylight Savings Time. The mission will lift off aboard Falcon 9's B-1081 booster, marking its 16th flight. B-1081 has supported high-profile missions like NASA's Crew 7 and CRS-29 and is set to land at Landing Zone 4 shortly after launch. Among the onboard payloads, NASA's Tracers satellites stand out. Part of the Small Explorers program, Tracers will study how solar wind interacts with Earth's magnetosphere, offering key insights into space weather, critical for satellite health, communications, and astronaut safety. Additional payloads include the PEXT demo, Athena Epic, REAL, Skycraft 4, and LIDE, each contributing to research across climate, Earth observation, and telecommunications. Though the delay was unexpected, it reinforces the importance of adaptability in modern spaceflight. With safety checks complete and launch preparations back on track, the mission promises to deliver valuable data that may help shape the next chapter of space science and exploration. Now, let us cap off today's updates and head a little further toward the pole, where a major development has just unfolded in Europe's Mars exploration program. In the Arctic region, the European Space Agency, better known as ESA, has successfully conducted a high-altitude test of a massive parachute system that is being prepared for the agency's upcoming ExoMars mission. According to ESA, this dual-stage parachute system is designed to handle the demanding task of landing scientific hardware on the Martian surface. It includes two separate parachutes. The first is 50 feet wide, or about 15 meters, and the second is an enormous 118 feet wide, or roughly 35. ESA has proudly stated that this is the largest parachute system ever designed for use beyond Earth. It is intended to slow down and safely land a descent module carrying sensitive equipment on Mars. This particular parachute system has had a long and difficult development journey. It has undergone multiple rounds of rigorous testing, including a number of test failures along the way. Despite these setbacks, the system was finally deemed ready for its original launch date back in 2022. Unfortunately, the mission was suspended following the geopolitical fallout from Russia's invasion of Ukraine. Because Russia had been contributing the landing platform and other critical technologies to the mission, ESA had no choice but to withdraw from the collaboration. As a result, the parachutes were placed in storage while Europe began work on an entirely new landing platform. Luca Ferracina, a system engineer for ESA's ExoMars entry, descent, and landing module, stated, "We are running this campaign to confirm our readiness for Mars and to verify that the parachutes are still performing as expected after the long storage." The goal appears to have been achieved with this recent Arctic test. Meanwhile, the broader future of the ExoMars mission has also been affected by financial uncertainties. Earlier plans involved NASA contributing hundreds of millions of dollars to assist ESA with the mission. However, the Trump administration's proposed NASA budget removed that funding as part of a series of science-related budget cuts. Fortunately, the U.S. Senate Appropriations Committee rejected those cuts in a report released on Friday, July 18th, suggesting that Congress may still support NASA's collaboration on ExoMars. ESA is watching these developments very closely, as a complete withdrawal of NASA's support could trigger further delays to a mission that has already seen many. In more recent progress, ESA signed a $194 million contract with Airbus to build a new landing platform entirely within Europe. As part of the parachute testing process, a mock-up of the descent module was lifted to an altitude of 18.6 miles or about 30 kilometers using a high-altitude balloon. This test took place at the S-Range Space Center in Kiruna, Sweden. After about 20 seconds of free fall, the first parachute deployed, simulating the aerodynamic forces the module will encounter while descending through the thin Martian atmosphere. While Mars has only about 1% of Earth's atmospheric density, ESA engineers carefully calibrated the test conditions to match the velocity and environmental factors expected during actual entry. Ferracina explained, "The combination of velocity and low atmospheric density in this test is exactly the same as what the parachutes will experience on Mars. During a real Martian landing, the capsule will enter the planet's atmosphere at an astonishing speed of 13,050 miles per hour or around 21,000 kilometers per hour. Natural drag will reduce this speed to approximately 1,000 miles per hour before the first parachute deploys. In the recent test, the mock-up capsule reached similar velocities during its brief descent through Earth's stratosphere." Ferracina concluded, "We are happy to confirm that we have a parachute design that can work on Mars, an ambitious system with the largest parachute ever to be flown outside Earth. It is clear that Europe is positioning itself as a serious contender in the ongoing race to explore Mars. With this successful test, the ExoMars mission takes a significant step forward, and the world will be watching closely to see what ESA accomplishes next." A new era for Starship is about to begin, marked by sweeping upgrades and a bold push toward the future. Standing at the center of this transformation is Launchpad B, a facility that has steadily risen from bare ground over the past year. Now, as construction nears completion, its final components are falling into place, signaling that operations may soon begin. But what exactly is changing at this critical launch site, and when will it come online? Pad A has been a critical asset in the development of Starship. From the earliest prototypes to all 9 integrated launches, this launch site has served as the backbone of nearly every major milestone in the program. But despite its importance, Pad A was never meant to support the long-term future of Starship. While its infrastructure remains functional, it lacks the design optimizations necessary for the next phase, especially as more powerful and complex versions of Starship come online. That is precisely why SpaceX has invested in the construction of a second orbital pad, Launchpad B. Built from the ground up with an eye toward future needs, this site features overarching upgrades across all major systems. The Orbital Launch Mount, or OLM, has undergone substantial structural improvements. The water deluge system has also been redesigned to better withstand the extreme thermal and acoustic forces generated during liftoff. And after more than a year of steady progress, Pad B is now entering its final stages of completion. One of the most recent and significant developments has been the arrival of the Booster Quick Disconnect Hood, a major structural element that protects the booster's fueling interfaces. On the 17th of this month, this hood was transported to the launch site, drawing immediate attention due to its size and design changes. Compared to the current version used at Pad A, the new BQD hood is significantly larger, likely to support the upcoming Starship V3 variant. These new vehicles will require higher volumes of fuel and more complex electrical and data connection, all of which must be managed by this upgraded interface. The shape of the hood also marks a departure from past designs. Instead of curving to fit the OLM, it now takes on a box-like form, suggesting it will be installed on a separate QD gantry rather than integrated directly into the OLM itself. This approach could offer more modularity and ease of maintenance. Additionally, the hood features large square openings on either end, which will allow for the installation of internal systems such as high-flow fuel lines and the retractable QD panel and thermal shielding. One of these cutouts even reveals a cluster of small ports which may be intended for auxiliary systems related to fueling or control. Still, the hood alone does not make up the full BQD. Several secondary components, like connector plates, shielding, and access doors, have yet to be added. The lack of visible latches or handles suggests that these parts are still in fabrication or will be installed later. Once assembled, the entire enclosure will protect the booster's fueling and avionics systems from debris and shockwaves during launch, especially important given the lessons learned from earlier missions like Flight 3. Beyond the QD system, other upgrades have been taking shape across Pad B. Notably, several manifolds have been added to the sides of the OLM, allowing for the routing of propellant and water between ground tanks and the pad. These new plumbing interfaces are a key indicator that fueling systems are nearly complete. The hold-down clamp arms, which physically restrain the booster prior to ignition, have also been upgraded. The Pad B OLM is equipped with 20 of these clamps, an increase from the initial 4 that were present when the mount was first seen at the Sanchez site. By early July, all 20 had been installed. These arms appear more compact and possibly stronger than their predecessors, suggesting they are designed to manage the higher forces expected from Starship V3. Every system added to Pad B has been engineered with redundancy, scalability, and environmental durability in mind. Since they are exposed to harsh conditions including salt air, rain, and high temperatures, their installation and testing must be exacting. With daily progress and near constant activity on site, it is clear that the pad is close to shifting from the build phase to the testing phase. So, when will Pad B officially come online? Given the pace of recent developments, it's possible that construction will wrap up by the end of this month. Initial tests will likely involve checking pipe pressure, valve responsiveness, and system connectivity. These dry runs will be followed by full-scale rehearsals and static fire tests, which could span 1 to 2 months depending on how smoothly everything proceeds. To validate these systems, SpaceX will need a test article. B-15, which has remained in reserve, is a likely candidate for early checks. Alternatively, Test Tank 17 could be brought in to simulate a V3 class Starship. This tank has been idle in the test cage for months and may soon be transported to the pad for preliminary integration. After these milestones are cleared, Pad B will be ready to support its first launch. While many expect it to debut with the powerful Starship V3, SpaceX may take a more measured approach. Flight 11, potentially using the last iteration of V1 and V2 hardware, could serve as a final test of the pad under known conditions before moving on to the more demanding V3 architecture. As of now, Flight 10 is projected for early August. Should it fly successfully, Flight 11 could lift off as soon as 1 or 2 months later. This timeline fits neatly with Pad B's expected activation schedule, suggesting its first use may occur sometime this fall. After more than a year of design, engineering, and construction, Pad B is poised to reshape the future of Starship. With stronger clamps, more advanced fueling interfaces, reinforced launch structures, and a modular approach to integration, this new facility is more than just a backup. It's the blueprint for SpaceX's next chapter. Will it support Starship V3 right out the gate, or will SpaceX opt for one final mission with legacy hardware to ensure a clean handoff? That remains to be seen. But what is certain is that Pad B is about to step into the spotlight, and as the launch window draws near, the entire spaceflight community will be watching. Yes, Pad B will be instrumental in shaping the next chapter of the Starship program. Pad A has faithfully served during the V1 and V2 development eras, but Starship V3 demands a bolder, more capable infrastructure. Pad B is the answer to that demand, purpose-built for the scale, power, and complexity of the next generation. With Raptor 3 engines now in play, delivering greater thrust and thermal output, the need for stronger, more sophisticated support systems is urgent, and Pad B delivers on all fronts. One of the most significant upgrades is the newly designed Orbital Launch Mount. The towering, long-legged structure used at Pad A has been replaced with a compact, robust platform, engineered to absorb greater stress and allow for easier upgrades. More importantly, the quick disconnect arm, which fuels and powers the rocket prior to launch, is no longer tied into the OLM itself. It now functions as a standalone system, providing enhanced flexibility and operational safety. Perhaps the most transformative feature of Pad B is its flame trench system. Instead of relying on a steel plate cooled by high-pressure water sprays, a method already showing signs of fatigue under repeated launches, Pad B incorporates a dual flame bucket design. This system redirects heat and pressure away from critical components, preserving the pad's structure even under the immense force of a Raptor 3-powered liftoff. Its effectiveness was proven at the Massey test stand, and Pad B takes the concept further, offering a scalable solution for frequent, high-intensity launches. This leap in infrastructure signals a shift in strategy. SpaceX is no longer just preparing for bigger rockets, it is preparing for more rockets. Pad B is designed with longevity and repetition in mind, enabling a far greater cadence than previously possible. Pad A, while still functional, is already showing discoloration and thermal wear. Modifications there are inevitable. SpaceX is expected to retrofit Pad A with lessons learned from Pad B, replacing the aging OLM and steel plate with a flame trench and updated systems. This will likely require Pad A to go offline, making Pad B the new workhorse of Starbase. Pad B's influence is already spreading. At Cape Canaveral's Launch Complex 39A, SpaceX has removed the old six-legged OLM design to implement a more advanced configuration echoing Pad B. Future systems at SLC-37 and additional Starbase sites are expected to follow suit. This isn't just an upgrade, it's the establishment of a new standard. Pad B is now the model for all future Starship launch infrastructure, and there is a lot of infrastructure to build. 3 major deployment plans are already mapped out. The first is a 25 launch plan originating from Starbase. Thanks to the existing hardware, this initiative is likely to begin first. With Pad B at the center of operations, the second phase is unfolding in Florida, where LC-39A and SLC-37 are slated for 44 and 76 launches respectively. These pads will eventually handle higher launch volumes than Starbase, but they require more construction, which means factories, integration bays, and support systems must all come online to establish autonomous operations. In the long term, even more launch pads will be built, each designed not just to support takeoffs but landings as well. The goal is a self-sustaining launch network capable of hundreds or even thousands of flights annually. Pad B is the foundation of that vision. Its layout, systems, and innovations are laying the groundwork for a global Starship launch architecture. New materials, more resilient mounts, smarter cooling systems, each improvement pushes Pad B closer to becoming the most advanced launch platform ever built. It's not merely a pad, it is a launch strategy incarnate, one that opens the door to higher reusability, greater efficiency, and missions of increasing complexity. As these systems are installed and refined, anticipation builds. Starship V3 is nearly ready. The launch pad that will carry it into this new age is nearly complete. Pad B will not only carry more powerful rockets to space, it will carry the ambitions of an entire company and perhaps one day an entire planet. We are witnessing the rise of infrastructure designed not just for one rocket, but for a generation. The dawn of large-scale, high-frequency spaceflight depends on systems like Pad B, systems that can endure, adapt, and evolve. Its influence will stretch beyond Texas. Pad B is the future blueprint, and its story is just beginning. Become a station, go to the moon, reach Mars. Now, Starship takes on a new role, Science Lab. SpaceX's Starfall initiative aims to turn Starship into an orbital platform for pharmaceutical research, using microgravity to unlock breakthroughs in medicine. It's a bold step, repurposing Starship from transport to innovation, but with the right upgrades, it could revolutionize both healthcare and spaceflight. The pace of launches has never been greater, and with each mission, our ambition grows bolder. No longer content with simply reaching orbit, we have set our sights on transforming low Earth space into a bustling hub of discovery. Pharmaceuticals, novel foodstuffs, cutting-edge materials. These are the raw ingredients of tomorrow's breakthroughs, and they demand the unique laboratory that only microgravity can provide. In this arena, Varda Space Industries has already staked its claim, but the true revolution begins where SpaceX's might meets visionary science. Every Varda capsule bound for orbit rides aloft courtesy of a Falcon 9, proof that SpaceX underpins the very foundation of in-space manufacturing. Now, in a move that could redefine both industry and medicine, SpaceX is forging its own path with Starfall, an initiative to deploy Starship as the ultimate orbital research platform. If Falcon 9 opened the door, Starship will burst through it. Starfall repurposes Starship from a transport behemoth into a floating constellation of experimental capsules. Imagine one launch, one Starship, delivering hundreds of sealed pods, each brimming with experimental drugs and compounds. Once in orbit, these capsules vent their restraints and begin independent missions, bathed in microgravity, untouched by atmospheric drag, and kissed by cosmic radiation. Here, proteins may fold in disruptive ways, crystals may grow unthinkably pure, and reactions may proceed with ineffable speed. True scale emerges when you confront Starship's gargantuan capacity. Today's payload champions struggle with a few dozen tons. Meanwhile, Starship promises 100 or even 200 metric tons to low Earth orbit. That means hundreds of Starfall capsules in a single mission, driving down per unit cost and shattering any hope of competition. Reusability underpins this vision. Starship's fully reusable architecture slashes costs per flight, crucial for an enterprise destined to launch again and again. Day after day, week after week, Starfall could run dozens of missions, each recovering its treasure pods, wrapped in heat shields and guided by parachutes back to Earth's embrace. Hence the name, Starfall, celestial experiments returning like falling stars. But Starfall is merely the opening chapter. Once aboard and breathing Earth's air, these capsules disgorge their payloads, pharmaceutical compounds primed for analysis, medical breakthroughs crystallized in the void. Food technologies can mature in true weightlessness, promising crops suited for Martian greenhouses. State-of-the-art semiconductors may arise, forged in conditions unviable on Earth. Even cosmetics, patches and creams born in orbit, may promise uncanny resilience. The implications are staggering. Cancer therapies refined in space, medications born of cosmic confluence, food systems designed for interplanetary settlers, materials to power everything from neural interfaces to fusion reactors, all incubated within Starfall's microgravity crucible. For SpaceX, the prize is both scientific glory and commercial gold. Commanding the frontier of in-orbit manufacturing elevates SpaceX to an unrivaled stratosphere of influence. Tens of billions in annual revenue? entirely possible once Starfall scales up. Those funds, in turn, drive down Starship's operating costs further, fueling a virtuous cycle of exploration and innovation. But Starfall also underwrites humanity's next giant leap. Long-duration missions to the Moon and Mars hinge on reliable pharmaceuticals and sustainable food sources. If Starship can become both delivery vehicle and life science foundry, then deep space outposts need never fear supply shortfalls. Even national defense stands to gain. The U.S. Space Force and U.S. Air Force already eye Starship for rapid logistics. Imagine Starfall capsules delivering life-saving medications to crisis zones worldwide in hours, not days, then returning precious research samples back to labs on Earth. A partnership between SpaceX and the Department of Defense could underwrite Starfall's launch manifest and cement Starship's role as a strategic asset. Yet colossal challenges lie ahead. Starfall demands partnerships, pharma giants, biotech startups, even sovereign governments. It requires regulatory approvals, orbital traffic management, secure re-entry corridors, and Starship itself must mature fully, its engines proven, its heat shields vetted, its launch cadence honed. Current indications suggest we are years away, 2028, perhaps 2030, before Starfall's first flight of hundreds of capsules. But momentum builds daily. Heat shield tests, capsule prototypes, mission planning sessions with research universities, each breakthrough edges us closer. Will Starfall revolutionize medicine? Can Starship evolve into the workshop of the gods, spawning cures and creations unimaginable on Earth? The next decade will tell. For now, we stand on the cusp of a new era, where rockets become research labs, where the heavens yield not only data but healing compounds, where the boundary between laboratory and launch pad blurs into a single soaring frontier. What do you think? Is Starfall feasible in our near future? Share your thoughts below, and if this glimpse of tomorrow excites you, like and subscribe to stay at the forefront of SpaceX's epic journey. It will take nothing less than a revolution in SpaceX's operations to turn Starfall from an audacious idea into a reality. On paper, transforming Starship into a floating pharmaceutical foundry feels natural. Microgravity unlocks chemical pathways unseen on Earth, and Starship's immense lift capacity, combined with rapid reusability, promises economies of scale. In practice, however, SpaceX must navigate an unforgiving gauntlet of technical, organizational, and regulatory challenges. SpaceX has never been a life sciences research operator. Its expertise lies in rockets and satellites, not in handling fragile biologics or automating complex laboratory experiments in orbit. Designing capsules that can cradle delicate drug compounds through launch loads, vacuum exposure, and re-entry heat is an engineering marathon. Each Starfall pod must be sturdy enough to shield its precious cargo, yet light enough to loft dozens of them in a single flight. Insulation, radiation barriers, miniaturized lab equipment, pressure seals, and fault-tolerant electronics must all fit into a shell that can ride Starship's ascent and later plunge back through Earth's atmosphere under its own heat shield and parachute. Every capsule becomes a tiny spacecraft in its own right, programmed to conduct its mission unsupervised and then guide itself home. The last point underscores another immense hurdle: autonomy. On the International Space Station, astronauts step in when experiments drift off course or instruments glitch. Starfall capsules will have no human hands on deck. They require robust sensors to detect leaks or hardware failures, intelligent software to reroute processes around malfunctions, and reliable communications to alert ground controllers when intervention is possible. A single valve stuck closed, a power glitch, or a software bug could corrupt months of precious research. SpaceX must pioneer new standards for autonomous laboratory operations, a level of resilience and self-healing never before demanded in orbit. Building these capsules and the supporting ground systems will soak up hundreds of millions, even billions of dollars before the first batch of space-made therapeutics return to Earth. Although Starship's reusability slashes launch costs compared to expendable rockets, the initial development of specialized containers, refurbishment facilities, and recovery operations across multiple ocean landing zones will carry significant upfront expenses. To defray those, SpaceX might seek partnerships with pharmaceutical giants or government agencies. But aligning commercial and scientific goals in this unconventional environment will be a delicate dance. Companies that have ventured into in-space manufacturing before may be wary of sharing hard-won protocols and trade secrets. As if starting a new division at the edge of space weren't enough, SpaceX must also master the core Starship technology itself. Starfall flights depend on Starship reliably reaching orbit, deploying payloads, and returning intact for reuse. So far, only Super Heavy has landed softly, and Ship has struggled with leaks, failed payload doors, and heat shield tile losses. The explosion of Ship 36 jolted the program's momentum, and Flight 10 must prove that Starship can complete fundamental orbital tasks like insert payloads, close its doors, reignite engines in space, and re-enter without ablating more tiles than it preserves. Only once those basics become routine can the company scale up Starfall capsules from a handful to the hundreds per mission that its business model demands. Regulation looms as a final gauntlet. Each capsule's launch and return must be licensed by the FAA. Today, a typical Starlink launch deploys dozens of satellites, each requiring coordination, but hundreds of Starfall capsules returning annually would multiply that complexity many times over. SpaceX must demonstrate that its operations pose no undue risk to people on the ground, no environmental hazard from reentry debris, and no interference with air traffic or maritime activities. Negotiating hundreds of reentry corridors, each with its own local regulations and environmental concerns, could stretch the approval process over years unless SpaceX forges proactive relationships with regulators. The timeline remains ambitious. Even as Starship proves its mettle, Starfall will take years of prototype capsules, iterative tests, and regulatory milestones before it can deliver its first batch of orbit-made therapeutics. Yet the momentum is undeniable, evident in Varda's early experiments, NASA's growing interest in commercial space labs, and SpaceX's unrelenting pace of launch innovation. Together, they point toward a future where every Starship mission doubles as a laboratory in the sky. Is Starfall feasible in our lifetime? The challenges are immense, but so is our capacity for ingenuity when driven by purpose. In the coming decade, we may watch a Starship launch hundreds of tiny capsules, each a ticking promise of medical breakthroughs. When they return, streaking down the atmosphere as falling stars, they will carry the seeds of tomorrow's cures, materials, and technologies. Proof that we are not merely passengers in space, but its architects. Starship will evolve from a mere transport vehicle into a thriving orbital research hub. It will pioneer pharmaceutical breakthroughs, forge trailblazing materials, and incubate technologies that reshape both space exploration and life on Earth. Imagine Starship as a factory in microgravity churning out life-saving drugs, next-generation semiconductors, and sustainable food solutions. By embracing this vision, SpaceX stakes its claim as the summit of space-based innovation. The path is strewn with technical, logistical, and regulatory challenges, yet SpaceX's history of overcoming the impossible offers reason for confidence. In the months ahead, every test flight and engineering milestone will reveal whether Starfall can deliver on its promise. If it succeeds, humanity's approach to research and development will transform, no longer bound to Earth but expanding into the final frontier. Watch closely, as SpaceX may soon turn this audacious dream into our new reality. Since 2023, a new giant has taken flight each year, reshaping the modern space race with fresh ambition and daring innovation, starting with Starship back in 2023, Vulcan in 2024, and now New Glenn in 2025. Soon, Rocket Lab's Neutron will join them. Rocket Lab made this evident, as it has unveiled a sea-based landing system for Neutron, mirroring SpaceX's drone ship method. Once revolutionary, this approach is now the standard to match and challenge. But Neutron is no ordinary rocket. It is Rocket Lab's answer to Falcon 9, aiming to rewrite the rules of reusability. Yet can it truly rival SpaceX? Let's find out today's episode of Great SpaceX. Rocket Lab is rapidly establishing itself as a bold and dynamic challenger in the competitive space launch industry. Unlike industry giants such as Blue Origin or ULA, Rocket Lab lacks the vast financial resources or long-standing government heritage. Yet through consistent innovation and successful missions, the company has managed to exceed expectations and secure a strong position just behind SpaceX in terms of annual launch cadence. Remarkably, all of this has been achieved using only its small lift rocket Electron, a vehicle that has proven to be both reliable and adaptable. Now, Rocket Lab has its sights set on a more ambitious future. At the heart of this vision lies Neutron, a next-generation medium-lift rocket that will be larger, more powerful, and most importantly, Reusable. Neutron is designed to meet the increasing demand for launching larger payloads, supporting constellation deployments, and carrying out high-assurance national security missions. Standing at 43 meters tall, this vehicle is poised to compete directly with rockets like SpaceX's Falcon 9 and ULA's Vulcan, but with a sleek design that blends efficiency and reusability. Recently, Rocket Lab revealed one of the most critical pieces of Neutron's recovery system, a sea-based landing platform. In a bold move that echoes SpaceX's pioneering approach with the Falcon 9, Rocket Lab announced that Neutron would land on a drone ship. The announcement was made on X, where Rocket Lab stated, "We've signed an agreement with Bollinger Ship to complete the build-out of our 400-foot landing platform for Neutron missions that return to Earth at sea, expanding our development of Neutron recovery infrastructure to Louisiana." Bollinger Shipyards, the partner selected for this project, is one of the largest privately owned shipbuilders in the U.S. Known for constructing high-performance marine vessels, Bollinger brings decades of experience in marine engineering and large-scale vessel construction. Their task is to convert a barge previously known as Oceanus into a high-tech drone ship tailored to Neutron's unique recovery needs. Rocket Lab's newly christened drone ship will be called Return on Investment, a name that perfectly captures the company's vision of leveraging reusability to drive down costs and increase access to space. The platform will be 400 feet long, or roughly 122 meters, significantly longer than SpaceX's Falcon 9 drone ships, which measure about 300 feet. This size difference reflects Neutron's unique proportions. While the rocket is slightly shorter than Falcon 9 at 42.8 meters, it features a much wider diameter, ranging from 5 to 7 meters. A larger drone ship not only accommodates Neutron's broader base, but may also support future innovations such as dual rocket landings or additional stabilization equipment. ROI will be outfitted with a suite of advanced systems designed for both precision and resilience. These include autonomous ground support equipment, blast shielding to protect onboard systems during landing, and station-keeping thrusters that allow the platform to hold its position in rough sea conditions. The platform will also feature thermal protection systems to safeguard sensitive electronics and support equipment, as well as custom Rocket Lab-developed hardware to secure and process Neutron once it touches down. Every element of the drone ship is being developed with a clear focus on stability, safety, and operational efficiency. Work on the platform is already underway at Bollinger's shipyard in Amelia, Louisiana, with a completion and delivery date targeted for 2026. This timeline aligns with Rocket Lab's broader plan to begin operational flights of Neutron within the next couple of years. Though Neutron's maiden flight is expected to take place before the drone ship is fully operational, the first mission will most likely end in a soft splashdown at sea. This trial will help Rocket Lab collect critical performance data before transitioning to recovery operations on the drone ship. Rocket Lab has also confirmed that Neutron's recovery operations will be based on the east coast of the United States, supporting launches from its facility at Wallops Island, Virginia. This proximity between launch and recovery zones will streamline operations and improve turnaround times, especially as Rocket Lab aims to scale its launch capacity rapidly. The decision to pursue sea-based landings marks a significant evolution in Rocket Lab's approach. Landing on a drone ship offers several clear advantages, particularly in terms of flexibility and fuel efficiency. Because the landing platform can be moved to optimal positions downrange, Neutron can complete its primary mission without needing to reserve large amounts of fuel for a return to launch site trajectory. This efficiency, paired with the safety benefits of conducting landings far from populated areas, makes drone ship recovery an ideal solution for high-cadence reusable operations. Moreover, Rocket Lab has made it clear that reusability is at the core of Neutron's design philosophy. In their update, the company emphasized, "Reusability is key to Rocket Lab's development of Neutron. To meet the increasing demand for regular and reliable launch to space for large single satellites, multi-satellite constellation deployment, and high-assurance national security missions, Rocket Lab expects to quickly scale Neutron and double its launch capacity annually once it enters service, with return on investment integral to that effort." This vision positions Rocket Lab as a serious contender in the evolving launch market. By adopting proven strategies from SpaceX, such as drone ship landings, while adding their own innovations and efficiency improvements, Rocket Lab is demonstrating a clear understanding of what it takes to compete at the highest levels. Neutron may still be in development, but every new announcement, from engine design to landing systems, brings it closer to reality. Rocket Lab's Neutron rocket is shaping up to be more than just another entry in the reusable launch race. Alongside its sea-based landing strategy, the vehicle itself is undergoing significant structural and architectural advancements that reflect the company's growing ambition to compete with the likes of SpaceX and Blue Origin. One of the standout upgrades is Rocket Lab's use of carbon composite for all major structural elements of Neutron. This material offers an ideal strength-to-weight ratio, which boosts efficiency during launch, flight, and landing. A lighter vehicle with enhanced durability improves performance and makes refurbishment between missions faster and easier, both critical for high launch cadence and cost-effective operations. Landing support is also being handled with careful engineering. Neutron will use static landing legs, a departure from the folding designs seen in other rockets. By eliminating complex deployment mechanisms, Rocket Lab reduces potential failure points while simplifying manufacturing and maintenance. The inclusion of forward fins will further aid in stabilization and trajectory control during descent, improving landing precision. Another notable feature is Neutron's stage separation system. Rather than the traditional stacked two-stage design, the second stage is enclosed within the first stage, housed inside a protective fairing. When separation is needed, the fairing opens just enough to let the second stage exit and ignite, then closes again. Nicknamed the Hungry Hippo, this mechanism allows the fairing to return intact with the first stage, making it recoverable. Most other rockets treat fairings as expendable or recover them separately. Only SpaceX has routinely attempted fairing recovery. Neutron's design fully integrates this process into the main recovery system, reducing turnaround time and complexity. This enclosure also protects sensitive payloads during ascent and contributes to more compact and lightweight structure. In essence, Neutron's fairing, second stage, and booster operate in a more unified, efficient configuration designed for rapid reuse. Powering Neutron is the Archimedes engine, fueled by liquid methane and liquid oxygen, commonly known as methalox. This clean-burning fuel is ideal for reusability and has become standard among next-gen rockets like Starship and New Glenn. Each engine uses an oxidizer-rich staged combustion cycle, delivering 74.8 tons of thrust at sea level and 90.7 tons in vacuum. With 9 Archimedes engines on the first stage, Neutron will lift off with around 673.7 tons of total thrust. The second stage will be powered by a vacuum-optimized version of the same engine. These capabilities allow Neutron to carry up to 15 tons to low Earth orbit in expendable mode and between 8.5 to 13 tons in reusable mode. This moves Rocket Lab into the medium lift market and gives them the ability to serve national security payloads, commercial constellations, and potentially crewed missions in the future. All of this innovation is being paired with a new sea-based recovery system. This large barge is being outfitted to handle Neutron's landings at sea with blast shielding, autonomous support systems, and station-keeping thrusters. Together with Neutron's vehicle improvements, it sets the stage for a fully reusable and flexible launch system. As Rocket Lab prepares for Neutron's debut, the company's intent is clear: to deliver reliable, rapid, and cost-effective access to space. Whether this is enough to challenge SpaceX's dominance remains to be seen, but the race is heating up. The potential of Rocket Lab's Neutron and its sea-based landing system is undeniable, but surpassing SpaceX remains an extraordinary challenge. The difficulty begins at the foundation. Landing on a drone ship is no small feat. To date, only SpaceX has successfully mastered this technique. Even Blue Origin, despite having immense funding and resources, has yet to deliver on its promise of recovering New Glenn via ocean-based landings. Rocket Lab must tread carefully and prepare thoroughly if it hopes to avoid similar delays or setbacks in this bold endeavor. Even if Neutron achieves its goal of a successful drone ship recovery, matching the scale and consistency of SpaceX's accomplishments is a distant milestone. SpaceX has now completed nearly 400 successful landings, most of which were at sea. Their recovery system boasts a high success rate, made possible through years of iteration, innovation, and real-world data. For Neutron to match that level of performance, it may take a decade or more, perhaps not even within this decade. Meanwhile, SpaceX continues to evolve with plans to expand the drone ship landing system to Starship. This would raise the bar even higher, potentially leaving the competition further behind. Still, in the broader space race, Neutron's prospects remain compelling. When compared to other competitors like Blue Origin, Neutron has a real opportunity to stand out. Rocket Lab, with just its small Electron rocket, has already surpassed Blue Origin in terms of launch cadence and reliability. The debut of Neutron, featuring a unique design, carbon composite construction, static landing legs, and drone ship recovery, signals a major leap forward. These advancements could give Rocket Lab the edge it needs to compete more aggressively in the medium-lift launch market. In this rapidly changing landscape, Neutron emerges as a symbol of ambition and innovation. The rocket may not dethrone SpaceX anytime soon, but it could outperform other competitors and establish Rocket Lab as the clear runner-up in reusability. With a clear vision and focused strategy, Rocket Lab is poised to make a significant mark on the future of spaceflight. The journey ahead will be difficult, but it is also filled with immense promise. This has been Kevin with Great SpaceX. Don't forget to like the video and subscribe if you haven't already to stay up to date with yours truly in the latest milestones in SpaceX's journey. Thank you so much for watching, and always remember, curiosity, imagination, and inspiration will follow you so long as you keep looking up.